In this video, we're going to work example problems where we solve compound inequalities. Specifically, these are going to be compound linear inequalities. Now, however, though, as we've been talking about, we do want to make sure we understand the big picture of all of this. So what is a compound inequality in general, not just linear? Okay, and so here we've actually, this is two separate compound inequalities. Here's one, and here's another. So this is like two problems in one here. Now, so we talked about, so what is a compound inequality? You might be tempted to say that, okay, well, that's the parallel to what we do with when we solve simultaneous equations. We're going to learn that in a few chapters from now. And I would caution you from making that comparison because, yes, it is similar, but there is differences too. Specifically because when it comes to simultaneous equations, you don't have like an and or an or statement, right? So that's very different, but it is similar in the sense that you are, when it comes to solving simultaneous equations, all we're going to be doing is, it's like we're going to have 1, 2, 3, 4, however many separate equations, and we're trying to find x values on the real number line or even in the entire complex plane that when you plug them in to each one of the equations, that same x value, it's a solution to all four of those equations at the same time. Then that's a solution. If it's just a solution to one or two and not the others, or three and not the other one, then it's not a solution. That's the idea of solving simultaneous equations, and again, it's not just two equations. It could be any number of equations you could be solving at the same, like looking for a simultaneous solution. And it is similar. Compound inequalities are similar in the sense that, yes, you are going to have to start by, so as we talked about, we can't really think about complex numbers in terms of inequalities at the moment. So you are going to start with finding a real number, all of the real numbers that, not just a real number, but all of the real numbers, because you get these big solution sets with inequalities, right? That it's going to have to satisfy this inequality and this inequality at the same time. You're going to start by doing that. You're going to be looking for the solutions to both of those. But it is different from simultaneous equations because we're dealing with inequalities. And so that's where you're going to have, you also have an and or an or associated with a compound inequality. Because you've got these big solution sets to these inequalities, and you're trying to see where do they cross over, or maybe you're just including everything in both. Okay, and so, but now when it comes to a compound inequality, you can have as many inequalities as you want. We could say, okay, so here's an inequality. This is a simple inequality, right? This looks like a solution to an inequality, but that's because we're starting off simple. Like we could say 2x plus 5 is less than 4, and 5 minus 3x is less than 7x. And then this needs to be satisfied, and then or for x, I mean, it could be any type of inequality. X squared minus or plus 3x is less than whatever, 2. So you need to find x values, all x values on the real number line, that when you plug them into this, it satisfies it. And when you plug them into this, it satisfies it. Or maybe it doesn't work in this at all, but it satisfies this, then that's a solution. You can't really have these and or criteria with equations. There's not enough solutions. Wouldn't make any sense. Equations always have just like one solution, two solutions, maybe 3 or 4. So you could kind of do that in some circumstances, think about ands and ors, but not really. These ands and ors only come into play with inequalities. Okay, but you see the criteria here, though, and you see how you could build anything you want. You could build up this complex array of ands and ors however you want with any number of inequalities, right? You see how this would be, okay, you plug it in here, and it doesn't satisfy this. Okay, but it still could be a solution if it satisfies both this and this inequality at the same time. Then it's a solution. Or maybe it's all three. Maybe it satisfies all three. That's a solution. Or maybe it satisfies this and not this. or this and not this, which means it fails this, but if it satisfies this, it's a solution. You see? And again, you can do this with any number of inequalities. Because we know how we've talked about how we can solve any kind of inequality, if it's linear, whatever. You bring everything to one side and find where the expression equals 0, where it's positive or negative. Those are the solutions. And so the idea is just going to be, how do you solve compound inequalities? Any kind of compound inequality, how do you solve it? What you're going to do is you're going to go to each inequality separately and solve it. And get the solution to that inequality. Then you're going to bring the solutions off to the side and write out the logic criteria. Like if the solution to this was x needs to be less than 6, then you'd say, okay, and the solution to this was x needs to be less or greater than 5, and then you had or x needs to be less than or equal to -2. Then you're just going to look at the solutions and you're going to condense it down as much as you can to the simplest form possible. Like if there's overlap, there might be overlapping. So you don't have to, like you could say if you had x is less than 5 and x is greater than 3, well, then you could write this as a compound. You could say x is less than 5. You could do it like that, right? Or if you had x is less than -2 and x is less than 10, well, then look at the overlap here. All you have to say is x is less than -2. You don't need the x is less than 10. Or if this was an or, then you could just say x is less than 10. You don't need the x is less than -2. That would be redundant in saying x is less than -2. So that's the process. You just solve every single inequality on its own, get the solution, and then rewrite the entire logic criteria tree with the solutions. And then just analyze the logic tree to see, okay, what's the simplest way I can condense this? What's redundant here so I can write the solution in the simplest way possible? That's the idea. Okay, so with that, let's solve this first inequality here. This is going to be compound where both are linear. So x needs to be less than 4 and x needs to be greater than or equal to -2. So this is, we're starting off simple here. This is like the step where we already found the solutions to the inequality. Okay, we've already found the solutions. Now we're at the step where we're comparing the solutions in regards to the specified logic and condensing it down as much as possible. That's it. So, okay, can we condense this down? Sometimes we can't condense it down. We just have to leave it as it is. But can we condense this down? So x is less than 4 and x is greater than or equal to -2. Well, okay, we can see what this is going to be. It's going to be everything in here. So yeah, we can condense this down. We can write this as a compound, a 3-part inequality. Like that. So this would be the final answer. Like if you had this on a test, that this isn't simplified yet. You need to put okay. Now, what about x is less than 4 or x is greater than or equal to -2? So, okay, x is less than 4, but this is an or statement. Okay, so yeah, this is, if we think about what does x being less than 4 mean? So we put a open parentheses here. Well, it's anything all the way to -infinity. Okay, what does x is greater than or equal to -2 mean? Well, it's anything, but it's an or statement. So the solution here is x can be anything. X is equal to, you could plug in any x you want, any real number you want, and it's going to be less than 4 or greater than or equal to -2. Think about it. You could pick any number in the entire number line. Is that number less than 4 or greater than or equal to -2? Well, yeah, no matter what you plug in, it's going to be. Okay, so now here, a little more complex. We've got these two separate inequalities here, or compound inequalities. Just note that these are two separate problems. Okay, but now we're starting off with it's not solved yet. Each inequality on its own is not solved yet. So we start by doing that. Let's subtract 1 from both sides here. 6 minus 1 is 5. Or let's multiply both sides by positive 3 here. Okay, and so we're going to do the other inequality is exactly the same. This is kind of confusing. It makes it seem like this is all the same problem. It's not. Okay, so now we're at the step where we've got the solutions. We just need to compare the solutions. So m being less than or equal to 5 or less than minus 6. Less than or equal to 5 or less than minus 6. This is redundant. This is redundant. So all we need to do here is say that m is less than or equal to 5. That's how we can condense this down. You see how this is redundant? Okay. M is less than or equal to 5 and m is less than minus 6. In that case, this is redundant. Now all we need to do is say that m is less than minus 6. Because if we're in this region, we're less than or equal to 5, but we're not less than minus 6. So this is an and criteria. So the solution to the first compound inequality is this. The solution to the second compound inequality is this. But I could turn this into one big compound inequality by doing this. Okay, what would be the answer to this entire compound inequality? Well, we'd be comparing these two. M is less than or equal to 5 and m is less than minus 6. Well, okay, that's kind of because it's the same inequality. So yeah, it's going to be okay. You could imagine that if maybe these were different, right? Maybe these two were different to start with. I mean, I could do this forever. I could just keep adding the same and just these same inequalities over and over again. But you get the idea. That would be the idea if these two were if these two inequalities were different than these two, then it's like if I put an and here, then I would be then comparing these two solutions with an and criteria. Okay, so let's see. Let's solve these two inequalities separately. So we've got, if we multiply both sides of this inequality by 2/3 or minus 2/3, we get y. We need to flip this. So minus 12 times minus 2/3, we've got positive 8. So, okay. Y is less than positive 8. And then we've got, so, and, but we're also going to do an or. Okay, 2.08 divided by 0.65 is 3.2. So y is less than or equal to 3.2. Okay, this is an 8. All right, so let's just now compare the solutions. So we've got, okay, we'll be more in the positive region. So 3.28. So less than 8 and less than or equal to 3.2. And, okay, well, the less than 8 is redundant. So this is y is less than or equal to 3.2. What about the or? Well, this is redundant. So there we go. Now, again, just note sometimes, I think we'll see some examples of this in upcoming examples of this, but sometimes you can't, you actually won't be able to condense it. Like this will end up being the final answer. Sometimes. Just note that. Okay, so again, these are two separate compound inequalities here. They just want us to practice with both the or and the and. So, okay, let's solve each one on its own. So 3x minus 6 plus 2 is less than or equal to x minus 8. So 3x minus 4 is less than or equal to x minus 8. Okay, subtracting x from both sides, we get, now adding 4 to both sides, we get, okay, dividing both sides by positive 2, we get this. Okay, now let's solve the other one. So we've got 4x plus 4 plus 2 is greater than minus 2x plus 4. Adding 2x to both sides. Okay, now 4 plus 2 is 6. Subtracting 6 from both sides. Okay, dividing both sides by 6. We get x is greater than minus 1/3. And there we go. So now we just want to compare these two with an, well, we'll start with an or and then an and. So, okay, let's see. We've got minus 2 minus 1/3. X is less than or equal to minus 2, or x is greater than minus 1/3. Well, you see there, that's would have to stay as it is. So the answer to this first problem would be, you can't change that. You can't condense it anymore, you see? And you could put that in interval notation as well. You could say minus infinity to minus 2, put a bracket at minus 2, in union with then minus 1/3 parentheses infinity. You could do that. Okay, now the and would be, let's see, there's no solution. There's no solution. There's never a, because you're all the way over here for x is less than or equal to minus 2. You're all the way over here for x is greater than minus 1/3. You just put a parentheses here and a bracket here. Well, there's no overlap. So there's no solution to the second case. Okay, this here was, this was called a three-part inequality. And all this is a special case of an and inequality, of an and compound inequality between two inequalities. That's what a three-part inequality is. It's a special case of a compound and inequality between two inequalities where you happen to have like this middle term is the same. But I want to stress, this is not the case. You can't write any and inequality like this. It's a special case where you're saying minus 3 is less than, or yeah, minus 2x plus 1, and minus 2x plus 1 is less than or equal to 9. Right? Now, the fact that you can see the minus 2x plus 1s both in the middle like that, you might not see that visually because we could have written this as, right, and you wouldn't necessarily see it. And, right, it's kind of hard to see when you look at it this way, but you just have to look closely and see that, okay, is there the same variable expression or number sandwiched in the middle? And then you can, you can combine them this way. It's a special case. Like we couldn't do that here. Here's an and inequality with just two inequalities, but there's no common value that you can sandwich in the middle. So it's just a special case where you're able to write these three-part inequalities like this. Okay? Now, we can actually do the properties of inequalities with a three-part inequality. So, and since we're dealing with this is linear, then we can actually go all the way to the end and without having to do like an analysis of the positive and negative intervals, etc. So using just this three-part inequality here. So that's pretty cool. So we can, if we want to subtract, like the equivalent to subtracting 1 from both sides here is you subtract 1 from all sides. So you get minus 3 minus 1. We want to isolate the x in the middle is the idea. Is less than minus 2x is less than or equal to 9 minus 1. So we subtracted 1 from all sides. So and that's why the 1 went away here. So we've got, okay, but now we want to isolate the x, so let's divide everything by -2, but since we divided by a negative number, we need to, that'd be +2, we need to flip each one of the inequalities. So, okay, but now let's just put this in ascending order. So let's just flip this. So we want to do that. And there you go. That's it. The final answer is this and. It's an and, right? X is greater than or equal to -4 and at the same time less than 2. Okay? So yeah, we can apply the properties of inequality here. So let's multiply this entire inequality by 2. That's positive, so we don't need to flip anything. Okay, let's add 4 to this entire inequality. So 4 plus 2 is 6. Okay, now let's divide everything by 5. We're not going to need to flip anything because 5 is positive. And there it is. Okay, let's multiply this entire inequality by -3. Okay, so, but we're going to need to flip the inequality symbols, both of them. So -12, okay. Let's subtract 1 from everything. So -13. Now let's divide everything by -2, but we're going to need to flip the inequality symbols again. So, okay, but now let's just put this in ascending order. So, or is it already in ascending order? Yeah, we're good. We'll just leave it like that. Like you want to have it looks cleaner if you have the smaller number on the left and the larger number on the right.